Welcome to this course on C++ templates. In this video, I'll be talking about what templates are and why they're important to the C++ programmer, and I'll also show you how to implement template functions and classes. This course is designed for beginning to intermediate C++ programmers. I'm assuming that you have at least 6 months experience of coding in C++, have a good understanding of object-oriented programming, and have a desire to learn. I am not assuming that you know anything about templates. Now, the course starts by investigating why we need templates, explaining the problems they solve and the shortcomings of existing solutions. Templates are a very important part of modern C++ coding, and there is hardly a library or coding idiom that doesn't use them. I'll briefly review some of the major areas in which they are used, such as containers in the standard library. You'll then see how to write and use simple template functions and classes, and I'll also explain how templates work and how they are processed by the compiler and linker. By the end of the course, you'll understand what templates are, why they're useful, and how important they are to modern C++. You'll be able to write and use function and class templates, as well as understand how they work. To start our exploration of templates, let's consider a very common problem: how to write functions that are identical apart from the type of their arguments. As a simple example, let's consider a max function that returns the maximum of its two arguments. The traditional way to do this in C would be to use a hash define, like this. Here we have a preprocessor macro called max that takes two parameters a and b. When used in code, the preprocessor will do a simple text substitution, substituting whatever you provide for a and b into the body of the macro. Because this is just a simple text editing operation and knows nothing of C++ syntax, we need to enclose the arguments and the whole expression in parentheses to ensure that everything works as we'd expect. This works all right for simple cases, as we can see here. If I compile and run this, we can see that this works. The max of 3 and 4 is 4, as we would expect. So it looks like it provides a definition of a generic function, but really this isn't a function, and you can see the problem if I use it in a slightly different way. Here I've declared two variables, x and y. Then I found the maximum, but what I've done is I've incremented x and y before using the preprocessor macro. If I run this, then we'll see that afterwards x is 2, but y is 4, showing that x has been incremented once, but y has actually been incremented twice. And this just underlines the fact that this isn't a real function call. In C++, we could get around this by using function overloading. For example, here are two versions of a max function, one that takes integers and one that takes doubles. If I try using these in code, let's run this and see what happens. We can now see that max of 5 and 6 is 6, absolutely, but I also used it with a pair of variables n and m that had values set to 1. When I run that, having incremented the variables, both n and m have been incremented once, as we'd expect. Of course, this works much better because we have real function calls, but we don't really want to have to create a new overload for each type. We can solve this problem using a function template. As the name implies, templates are patterns for creating functions and classes whose code is identical but which differ in parameter types and values. But before we dive into showing how to use them, let's discuss templates in a little more detail for a couple of minutes. Templates were one of the features that Bjarne Stroustrup wanted C++ to support from very early in its life, and he discussed several advanced features, including templates, virtual functions, and multiple inheritance, as early as 1982. The concepts behind templates were documented in the Annotated Reference Manual, written by Ellis and Stroustrup and published in 1990, and the first version of C++ to support templates was CFront 3.0 in September 1991. At that point, other vendors were releasing C++ compilers, but it was quite a long time before everyone reached the same level of implementation, and in the 90s, templates gained a name in some quarters for being buggy and badly implemented. And for many, they were a curiosity that didn't make its way into mainstream OO programming, apart from very simple use in container types in vendor-specific libraries. That changed with the release of the first standard in 1998, which brought the new standard template library firmly into the foreground. This made heavy use of templates, and for the first time, many C++ developers had to understand what templates were and how they were used. The next milestone for many was the publication of Andrei Alexandrescu's Modern C++ Design in 2001, in which he described a number of advanced programming techniques that relied on templates. This was so advanced in its use of templates that for some time there were very few compilers that could compile his libraries. I think it's true to say that this book opened a lot of people's eyes to what templates were capable of doing. Today, templates are a very important part of modern C++, and it isn't an exaggeration to say that you're unlikely to see a piece of modern C++ code that does not involve templates in one way or another at almost every step. And that brings me to the topic of template metaprogramming, or using the template system to perform computation at compile time. During the standardization process, the template system was found to be Turing complete, so you can write programs in it that the compiler will run at compile time. This was demonstrated, not intentionally, by Erwin Unruh in 1994, when he wrote a program to calculate prime numbers and discovered via error messages that the compiler was trying to calculate them compile time. The book C++ Template Metaprogramming by Abrahams and Gertovoy introduced this topic to a wider audience in 2004, and the Boost MPL library is widely used. We'll look briefly at metaprogramming later in the course. Generic programming also uses templates and uses a type's capabilities rather than the base class it extends or the interfaces it implements. Take a simple iterator as an example. This could expose ++ to move to the next value, asterisk to dereference, and equals for comparison with other iterators. The very interesting thing here is that these requirements can be satisfied in several ways, in particular by a traditional pointer or by a class that implements the right operators. Now, those two have nothing in common, and generic programming uses templates that specify behavior, and any type that provides it can be used. We'll talk more about this towards the end of the course. Now, anyone who's coded in Java or C# may think that templates are the same as generics in those languages. Although there is a superficial similarity in the syntax and the way that they're often used, both using angle brackets to hold type parameter information, they're completely different in mechanism. Templates in C++ are a compile time mechanism for generating code, while generics in Java and .NET are not. Now, as with any language feature, templates have advantages and disadvantages. Perhaps the main benefit of templates comes from improved runtime performance. This is often due to static polymorphism, which can eliminate the need for virtual function calls. Templates are used in the STL to provide efficient type-safe container classes, and they're also the basis of policy-based design, which uses multiple inheritance from template-based classes. Improved runtime performance can be achieved by using templates to perform calculation at compile time. And finally, templates also bring general improvements in type safety at no runtime cost. A good example of this is the use of variadic templates to implement tuples. We'll talk about a number of these advantages in more detail as the course progresses. Now, of course, although templates are very useful and widely used, they do have some downsides. Heavy use of templates brings the possibility of much longer compile times, and on large code bases, this can run into hours. Template instantiations can lead to code bloat, especially when using non-type template parameters. Templates can be hard to debug when things don't go right. How do you debug something at compile time? There are some tools to help, such as Templite for the Clang compiler, but it can be very hard to diagnose problems with template instantiation. Part of this is due to the fact that error messages related to template instantiation and use are frequently terrible and often give no insight at all into what the problem might actually be. Last but not least, it can be hard finding developers who really understand this stuff. But once you finish this course, I hope there'll be a few more of you around. Before we move on, let me just tell you about some useful reading material. C++ Templates, The Complete Guide by Van der Voorde and Jasoutis is a very good guide to templates and how they work. It's a little old now and doesn't include a lot of the latest stuff from C++ 11 and 14, but it is still a complete guide to the basics of how templates work and well worth consulting. I've already mentioned this book, Modern C++ Design by Alexandrescu, which really laid the foundations for modern C++ style. Template metaprogramming was introduced to many C++ developers through this book, C++ Template Metaprogramming by Abrahams and Gertovoy. If you're interested in that topic, this is a very good read. Then we've got Effective Modern C++ by Scott Mayers. His books on Effective C++ are classics, and he's updated Effective C++ to show us how to make use of a lot of the stuff that's come in C++ 11 and 14, and that of necessity includes a lot of template material. Then there's the C++ standard library reference by Nikolai Jasoutis. The standard library is heavily based on templates, so this is a very good guide to how to use the classes and functions within the library. Finally, if you're really interested in template metaprogramming, Advanced C++ Metaprogramming by David Giugiaro will show you exactly what you can do with this very interesting technique. Here's a template version of our max function. Disregarding the first line for a minute, the function code is exactly as you'd expect, except that the parameter and return types have been replaced by t. This is a marker showing the function's parameter and return types, which in this case happen to be the same. The compiler knows that t is a marker because of the first line. The keyword template introduces a template definition, and the markers, known as type parameters, are placed after it in angle brackets. You can call the type parameters anything you like, and it has been traditional to use capital letters starting with T. I'll explain later when you might want to use longer and more expressive names. Note that the function both takes and returns const references. We know that using references avoids the overhead of creating and destroying temporaries, and using const references means that this function can be used with literals. There are a couple of other reasons why I implement this using const references. The max function is being used to compare values and is not concerned with identity. And so pass by value does what we require, and using const references avoids the possible overhead of a copy. The second reason concerns immutability. You may well be aware of how interest in functional programming has increased in the last few years, and it can feel like the latest bandwagon at times. However, there are real benefits to working with immutable data as much as possible, especially in concurrent code, and using const references fits with that idea. Now, I've just said that T is a marker standing for a type that will be known at compile time. In theory, you can use any type with this function template. But when you look at the code, you'll realize that there is a constraint on T, and that is that the greater than operation must be valid. Note that I don't say that T must have a greater than operator. It is possible that there could be an implicit conversion to a type that supports it. And as usual with implicit conversions, this could lead to the odd surprise. Later in the course, I'll discuss how features added in C++11 make it possible to control precisely the types that can be used with template functions and classes. Let's use this in code. Here I've got a couple of integer variables, and I'm going to use it to call the max function. Let's see what happens. As you'd expect, it calculates the max of those two numbers as 4, which is fine. When the compiler sees a reference to max, it first checks to see whether there is a non-template function with the right signature, and if so, it uses that. It only generates code from the template if it can't find a function that fits. I can demonstrate this by adding a specific implementation for int, and what I'll also is just add a little bit of output to the template version so that we can see which one's being called. If I now add another line to main, I've now got two calls to max, one of which takes two ints and one of which takes two doubles. Let's see which one gets called. Now we can see that when I pass int, it calls the int version, but when I pass doubles, it generates a double version from the template. What we can see here is that template functions can be overloaded as usual, and I'll have more to say about that later. What happens if I call max with different types? Let's try it, for example, with an int for the first parameter and a double for the second. When I build this, the LLVM compiler gives me a warning saying that it's converting double to int, which changes the value from 4.6 to 4. The reason for that is that I've got an explicit int version of the function. The compiler uses that, and it applies the usual rules for argument coercion. However, if I comment out the int version and rebuild, now I get an error saying that there's no matching function for the call to max, and the reason is that the template requires two arguments of the same type, and conversions aren't done when deciding how to process templates. Now, I could fix that if I wanted by telling the compiler to instantiate a particular version of the template. And if I now build, it builds cleanly, and if I now run, it's used the template version and given me the answer I expect. Just a moment, let's just look up here. We've seen so far the use of the class keyword, but you'll often see another one used, and that is type name. And if I just put that in here, template type name T. In this context, they mean exactly the same thing. Bjarne Stroustrup, originally used class in order to avoid introducing a new keyword into the language. Type name was added later on for another purpose, but it was decided to use it here as well to avoid any idea that T has to be a class and can't, for example, be a built-in such as int. So it's recommended that you use class if the template parameter does have to be a class, and type name otherwise, and that's the rule that I'll follow from now on. The template functions I've written so far have had a single template parameter, but you can, of course, create template functions with more than one. Here's an example. This function takes two arguments, which may be of different types, and returns a Boolean. This, of course, relies on there being a suitable implementation of greater than available. And here's a question to think about. What if we have a function whose operation depends in some way on the argument types? One example might be calculating an area, which you can, given two arguments of type meter, might need to use a temporary variable of type meter squared. Given that the compiler knows nothing about those types at compile time, how can it decide what the type of the temporary variable should be? We'll see later in the course how C++11 has added functionality to support this. To round off this chapter, let's take a couple of minutes to consider how the C++ compiler generates template code. The process can be quite complex, but in essence, the compiler will generate template instances on first call and then use them when it finds a call with the same template parameter types. In the example code here, on the first call to max, the compiler deduces the parameter type and emits the object code for an int version. Any subsequent calls to max with int arguments will then use this version. Another call uses double, which will result in a double version being instantiated, and so on. So let's see what the compiler actually does. We can investigate the generated code by running nm on the binary. nm is a Unix utility that can display the symbol table for an executable or object file. When I run it on this binary, we can see that there are a lot of symbols there. Let's focus on this a little bit more and look for max. And we can see that there are two entries for max, but the names are mangled so that it isn't easy to see what they represent. Let's try unmangling them. So if I copy that, there is a utility called C++filt, which will unmangle names. And if I look at this, it shows me indeed that this is a template instantiation for double. You can see that the second name actually only differs from the first one by this lowercase I, and that shows that that is an int version as opposed to this double one. Now, the compiler may produce multiple instantiations of a template in different compilation units, and the linker somehow has to ensure that only one of them occurs in the final executable. How that's done is implementation dependent, but it is a solved problem. Now, there's a very important point to note here. In order for the compiler to be able to instantiate templates, it has to be able to see the template source code. For this reason, you'll see template code included in header files, and you only have to look at a typical library header such as IOStream to see just how large these can get. Good practice says that you don't include headers that you don't need to save the compiler parsing many thousands of lines of code that it may not then need. Poor discipline when including template headers can greatly affect compilation times. As an exercise to test out what you've learnt, try implementing a function to swap two values. What will be the best way to pass the arguments, and what are the constraints on the type parameter? Then implement a function to find the sum of an array of numbers. If your type parameter is t, you can use t with empty parentheses, and this will get you a default value for that type. Try testing it with different numeric types to see that it works. It should be no surprise that you can create template classes as well as functions. This is especially valuable for containers, where the operation of the container is the same regardless of the type in the container. For many people, this is their main use case for templates, but as we'll see later on, there are many other uses to which template classes can be put. Let's start by creating a simple template container, a stack. We start the definition with the template keyword, as you'd expect. So our stack is parameterized on type T, and internally is going to hold its data in a dynamically allocated buffer. Let's add code for construction and destruction. When we construct a stack object, we specify the size, we save that size and allocate a buffer. And when the stack object is destroyed, it frees up the memory. Note the C++11 universal initialization syntax, which uses curly braces for initializer expressions. We'll also need a member to track the top of the stack. Let's put that in. Now got a member current, which is initialized to 0. So far, so good. Now for the operations. As you'll be aware, a stack supports two fundamental operations, push and pop, but I'm going to implement three, push, pop, and top, and I'll explain why in a minute. Push takes a const reference to a t and pushes it onto the stack. Top returns the top value on the stack but doesn't remove it, and pop removes the top value and doesn't return it. You may be wondering why pop doesn't remove the top value as well as return it. The reason is that there's a nasty problem with exception safety here. Suppose we go with a really simple implementation of pop. Current points to the next free position on the stack. So the top value will be at position current -1, and we need to adjust that value so that we'll be able to reuse that next time. Where's the problem? Well, we don't know what type T could be. So returning by value might invoke a copy constructor. This could fail and it could throw an exception. But if it does, we've already changed the value of current and the state of our stack object has now been corrupted. You can try rewriting the code, but it really isn't simple to arrange things so that if the copy constructor fails on return, the current value hasn't been changed. The solution is to divide the pop operation into two, so that top simply returns the top value. So let's see that. If returning the value throws an exception, then the value of current hasn't been changed and the state of the object is consistent. On the other hand, pop simply decrements the value of current, thus resetting the top of the stack. And that decrement can't fail. Because I've added exception handling, I ought to add my stack exception class. So let's put that in. Here's an exception class, and I'd like to point out a couple of things. The first is that the class inherits from standard exception. Although you can use anything as an exception object in C++, it's good practice to use types that are part of a standard exception hierarchy. And the second is the use of the noExcept and override modifiers on the what function. These were introduced in C++11. NoExcept is used on functions that do not throw any exceptions. If such a function does, then terminate will be called. An override shows that this is intended to override a virtual function in a base class. You will get a compiler error if that is not the case. All I need to do now is add my implementation of push. And we can see here that once again, I've separated manipulating the data item from adjusting the value of current. So if the assignment throws an exception, the value of current hasn't been altered and we're in a consistent state. As I remarked earlier, in contrast to non-template types, in order to be able to use a template class, the compiler has to be able to see the code and not just the declaration. So I can put the whole definition in a header file, as I have here, with an include guard, of course, and the code will run exactly as I expect. As an aside, people have long wanted to be able to define template code in separate source files and not have to provide it in headers so as not to have to parse all this implementation. There was an attempt to do this using the export keyword, which would tell the compiler that the template was defined elsewhere, but this hasn't ever been seriously implemented. Export is, however, still a keyword, even if it isn't currently used for anything. One thing to note while we're here is that when we implement the members of our template class out of line, we have to say that they belong to stack of T and not to stack. There isn't a class called stack, only a generic type called stack of T, so that needs to go in here. Of course, it's very common to see template classes defined like this, but if you want, you can of course define members inline inside the class itself. Let's just do that. For instance, let's just take push, copy that, then let me comment out the existing implementation, and I'll go up here. Now I have an implementation of push inside the class itself. Lots of people do this. The only possible disadvantage is that you end up with a lot of highly nested code inside your class, but which you prefer is up to you. So now all the code is in place, let's try using the stack. I'll create a stack of ints called s of size 10. Unlike a template function, the compiler cannot tell from context what the type parameter should be. So I need to tell it by providing that information in angle brackets. And as with template functions, this causes the compiler to generate a version of stack complete with all its member functions with int as the template parameter. Now let's try using it. I've now pushed some items on. Let's see what the top one is. Now let's remove the top one and we'll go back and see what the top one is now. Let's build this and we'll run it. And it says that the top was indeed 30. And then when we removed it, the top was 20. Finally, let's just take a look at what's been generated. Once again, I can run nm on this binary. As you can see, I'm in directory here, nm0301 on the binary, shows me a lot of detail, but let's have a look for ones that mention stack specifically. And you can see here that we have a whole load of entries that mention stack: pop, top, push, and another whole load. Let's run this through C++ Filter. And we can see that this is an implementation of pop for the stack class. If I just pick another one here, we'll try that as well. And that is the destructor. You can see exactly how the code has been generated. So as an exercise to test out what you've learned about template classes, modify your stack so that it doesn't have a fixed size. You'll need to reallocate memory as necessary. So what will the default size be, and what strategy could you use for reallocation? You only need in this exercise to consider primitive types for T and not classes. And as a hint, if you're thinking about reallocating memory, consider the realloc function. In conclusion, let's look at what we've covered. We started by looking at what templates are and the part that they play in modern C++ programming. We then looked at how to write and use template functions and classes, and also discussed the mechanism underlying how they are processed at compile time. So where do you go from here? Two things are key to improving as a developer. Reading both written material and posts on the web will expand your knowledge, and experimenting by writing code will often show you that implementing something you think you understand isn't quite as simple as you thought. You'll also find that the other videos in this series will take you further in your understanding of what templates are and how to use them. Just remains for me to say that I hope you've enjoyed our brief exploration of C++ templates, and to thank you for watching.